Hi there, my name is Miss Benson, and I am the Math 1610 or College Algebra Coordinator here on campus. In this video, I'm going to be giving you your Section 1.1 lecture on functions, properties, and graphs. Now, since this is the very first lecture of the semester, you're probably not super familiar with the layout of the guided notes, so I wanted to take a moment just to explain a few things. So first of all, you'll always see the title up here, Section 1.1, Functions, Properties, and Graphs. Then there's a length. That's not always accurate. Sometimes we have 1 day for this lesson, sometimes we have 2, but that's just generally what we have. So for example, in spring 2025, the Monday, Wednesday class has 1 day to do it, the Tuesday, Thursday has 2. It just falls that way sometimes, but just know that's a general assumption about how many days it will take to cover this lesson, but we are going to do it in one video today. Second, you're always going to see a quick quiz at the start of each lesson. So the quick quiz contains prerequisite material that you need to be successful in this lesson. Ideally, you would complete the quick quiz prior to the lesson, check your answers, and then come into the lesson with that familiar knowledge in your mind. So if you haven't already done so, go ahead and pause the video, see if you can do quick quiz questions 1 through 4, and then check your answers. So the answers to every quick quiz will be at the very end of that section of guided notes. So let's see. Yep, here's the end. Here it is. Here's the end of section 1.1. So you can see there are the 4 quick quiz answers. So you'll work the questions, check your answers, and you can always email your professor or go to the math lab if you have any questions. But for now, let's go ahead and get started with our guided notes on section 1.1, functions, properties, and graphs. So as you watch this video, have these notes in front of you and be following along with me, filling in your blanks and working out the problems. Let's start with some critical terms. So a set of ordered pairs, x, y, is called a relation in x and y. The set of x values in the ordered pairs is called the domain, and the set of y values in the ordered pairs is called the range. So you've probably heard those terms before. A set of ordered pairs has an x and a y in each ordered pair. The set of ordered pairs is referred to as a relation. The set of all x's is the domain, and the set of all y's is the range. So let's take a look at our first example. Example 1 says, for the table shown, complete the following. A, write the set of ordered pairs that defines the relation. So first we're just going to write the set of ordered pairs. You can see this is the x line and the y line. And we'll put our ordered pairs in a set of curly braces and separate them with commas. So the first ordered pair is 3, -4. The second one is -2, 0. The third is 5, 3. And the fourth is 1, 0. That's all they wanted us to do for part A. Part B says write the domain. Okay, so we will also list the domain in a set of curly braces, but the domain is just the set of x's, so we won't need the parentheses. We'll just need the x's separated by commas. So that would be 3, -2, 5, and 1. You can list those in numerical order if you'd like to, but you don't have to. And then C, write the range. So same thing, except the range is the set of all y values. So you'll notice that we have 2 y values that repeat. There are 2 zeros, this one here and this one here. We're not going to list it twice when we list our range. We'll just list it once. So we'll say -4, 0, and 3. And for example 1, that's all they want us to do. List the set of ordered pairs, state the domain, state the range. Let's see what's next. We have another critical term. It says, given a relation in x and y, we say that y is a function of x if for each value of x in the domain, there is exactly one value of y in the range. Now that is the formal definition of a function, but it's important that we know the practical definition of a function as well, because we need to be able to apply it to specific problems. So this box underneath the critical term, it gives us the more practical definition that we can actually apply to problems. It says this means that in a function, x values cannot be repeated, but y values can. So if we are looking at a set of ordered pairs, for example, like we're going to look at in example 2, it's a function as long as the x values don't repeat. I don't care what the y values are doing. The y values can repeat as much as we want them to, but the x values cannot repeat. So let's take a look at example 2. It says, determine if each relation defines y as a function of x. So this keyword tells me to reference this box. I want to make sure that for the set of ordered pairs in A and the set of ordered pairs in B, that those are functions, meaning that no x values repeat. So let's look at A. Remember, I don't care what the y values are doing. The x values are 8, 3, and 5. X values don't repeat, so I say yes, it is a function. If the x values did repeat, then I would say no. But none of the x values repeat, they're all different, 8, 3, and 5, so yes, that's a function. We'll change colors for part B. Let's look at the x values given in B. -3, 9, 1, -3. We have a repeated x value. The x value of -3 is repeated in this relation. So we would say, no, this relation is not a function. So A shows a function, B does not show a function. Let's look at another way that this question can be presented. So you can be given a relation that is a set of ordered pairs and asked whether or not that set is a function. But it can also be presented like this, almost as a chart. So you can see the directions are exactly the same for example 3. Determine if each relation defines y as a function of x. So when you look at this, do you see how this -7 here, there are 2 arrows coming from it? So it tells you this bubble is the x's. But you can think of this as -10, -7, -7. There are 2 arrows coming from -7. Therefore, the x value, -7, is repeated. Well, we can't have repeated x values. So we would say no. This one is not a function. Remember, we don't care what the y's are doing. What makes it a function is that the x values do not repeat. So let's look at B. We have 6, 1, and 10. And if you look at this diagram, each of those x values have only 1 arrow coming from them. So that means they're each distinct or they're not repeated. So we would say yes, this diagram, picture, chart, whatever you want to call it, demonstrates a function or shows a function. Okay, so that takes us through example 2 and example 3. Let's do some more critical terms. Let's talk about the vertical line test. Okay, so that's your blank here. The vertical line test is used to determine if a given graph defines y as a function of x. The graph defines y as a function of x if no vertical line intersects the graph at more than one point. Okay, so let's talk about this real quick. You can see, look at the directions for example 4. You can see they're exactly the same as examples 2 and 3. Determine if each relation defines y as a function of x. So you learned how to answer that question if you were given a list of points. You learned how to answer that question if you were given a chart. So now we're going to learn how to answer that question if we're given a graph. If you are given a graph and you're asked the question, does this graph show a function? Well, then you just have to do the vertical line test. So when you do the vertical line test, you imagine a million vertical lines being drawn through the graph that's in front of you. If any one of those lines passes through the blue graph, or whatever color it is, here it's blue, but passes through the blue graph more than one time, then we would say, no, it's not a function. If all of those vertical lines pass through your graph only one time each, then it is a function. So determine if each relation defines y as a function of x. If I drew a million vertical lines through this graph on part A, all of those vertical lines would only touch the graph one time. Therefore, we say, yes, this one is a function. However, it's very obvious here that if I draw this vertical line here, it passes through this graph 3 times. Well, that's definitely not a function. Even if it only passed through twice, it would still not be a function. So we'll say no. Graph A demonstrates a function. Graph B does not demonstrate a function. All right, let's see what example 5 has in store for us. So example 5 says, determine if each relation defines y as a function of x. Okay, same directions again. So we now have 4 different questions with the exact same directions. The first one gives you a list of ordered pairs and says, is it a function? The second one gives you a chart and says, is it a function? The third one gave you a graph and said, is it a function? Now I'm going to give you an equation and ask you the same question. Is it a function? So determine if each relation defines y as a function of x. So there's a couple of different ways you can think about this, but probably the most straightforward is that each input should give you only one output. Okay, so let me give you an example. If I input an x value of 1, for example, okay, let's use 1 as our baseline. If I input an x value of 1, I should only get out a single y value. Let's see if that happens. Let's look at part A. It says y equals 2x plus 7. So y equals, let's plug in 1. Let's do x equals 1. 2 times 1 plus 7. Okay, that's y equals 2 plus 7, which is y equals 9. So I'm going to use a highlighter so I can kind of show you what I'm talking about, especially since you're not directly sitting in front of me and watching it on a video instead. But see how I put in a single input and I got out a single output? That tells me it's a function. A single input gives me a single output. Okay, let's try another one. Y squared equals x. Let's plug it in again. Y squared equals 1. To solve that, I would square root both sides. But the thing is, when you square root both sides of an equation, you have to put a plus or minus in front of the numerical side. So that gives me y equals plus or minus 1. So that's 2 y values. That's a y value of -1 and a y value of +1. So I put in, let's get my highlighter back. I put in a single value of 1 and I got out 2 values for y. I put in a single x value and got out 2 y values. That means this is not a function. So this would be no, because a single input gave me 2 outputs. This would be yes, because a single input gave me a single output. Okay, let's do it one more time. So again, we're going to use x equals 1 as our baseline. So y equals the absolute value of 1. Let's see if I can write that a little better. The problem is my 1s look like my absolute value bars, which is not helpful for anybody, but here we go. Let's see if I can write it a little better. All right, the absolute value of 1 is 1. Okay, so I plugged in x equals 1 and got out y equals 1. Again with the highlighter, I plugged in x equals 1 and got out y equals 1. So a single input gave me a single output. So I would say for this one, yes, it is a function. So I would say of the 4 questions that have these directions, determine if each relation defines y as a function of x, I would say this one is the most complicated because you have to sort of use a test value and show that a single input gives you a single output. But I can give you some hints too. So y should always have a power of 1. Do you see this y here in y equals 2x plus 7 has a power of 1? This y here and y equals the absolute value of x has a power of 1. Y should always have a power of 1, or at least an odd power. Okay, anytime that your y has an even power, like it does in part B, y squared equals x, that's usually going to give you more than one output or more than one y value. So typically, if y has an even power, it's going to be no. But if y has 1 as its power, it's going to be yes. So kind of a hard question, but if you need some clarification, like I said before, you're welcome to go to the math lab and ask a tutor, or you can email your professor. But for now, let's keep going. Let's see what's next. So example 6 says, evaluate the function f of x equals negative 2x squared plus 6x minus 3 for the given value of x. So we're treating this like 3 separate problems. In part A, we're finding f of negative 7. In part B, we're finding f of t minus 3. And in part C, we're finding f of x plus h. So let's start with A. F of negative 7. Now remember, they gave us the function f in the directions. F of x equals negative 2x squared plus 6x minus 3. So that just means we take whatever's in the parentheses, in this case negative 7, and plug it in for x. So negative 2 times negative 7 squared plus 6 times negative 7 minus 3. You can plug that into your calculator, but once you do, you end up getting negative 143, which is our answer. All right, let's do B in a different color, just so we don't get confused. This time we're calculating f of t minus 3. So everywhere I see an x in the original problem, I'm going to put a t minus 3. So f of t minus 3 is negative 2 times t minus 3 squared plus 6 times t minus 3 minus 3. Okay, let's simplify that a little bit. Remember that t minus 3 squared means t minus 3 times t minus 3, because to square something means to multiply it by itself. That's why 5 squared is 25, because 5 times 5 is 25. So to rewrite this, we have negative 2 times t, minus 3 times t minus 3, and I'll just carry down the rest of it, plus 6 times t minus 3 minus 3. So I'm going to FOIL this part right here. Negative 2 times, remember FOIL is front, outer, inner, last. So t times t is t squared. T times negative 3 is negative 3t. Negative 3 times t is negative 3t, and negative 3 times negative 3 is positive 9. So what I've done so far is take this negative 2 and carry it down, and then I FOIL this out into this. I still need to bring the rest of this down. So we have plus 6 times t minus 3 minus 3. So now what I need to do is take this negative 2 and distribute it to its set of parentheses, and simultaneously take this 6 and distribute it to its set of parentheses, and then I'll just carry down the minus 3 on the end. So we have negative 2 t squared, let's see, plus 6t plus 6t. Oh, look, I forgot an arrow. Not that it really matters, but let's be consistent. Then negative 2 times 9 is minus 18. So I distributed the negative 2 to its set of parentheses. Now I'm distributing the 6 to its set of parentheses. Plus 6t minus 18 minus 3. And now I'm going to combine like terms. So I don't have any other t squared, so I'll just do negative 2t squared. Okay, that took care of this one. Now 6t and 6t and 6t is 18t. So plus 18t. That took care of those three. And then negative 18, and negative 3 is negative 39. And that is as simple as I can get. So the answer to part B, when I plug in t minus 3 and simplify, is negative 2t squared plus 18t minus 39. Now I want to just take a second to remind you of the beauty of having this lecture on a video. If you need to pause the video to rework the problem yourself, or even rewind the video and listen to the explanation again, you certainly can do that. Or you can email your professor and ask questions. But make sure that you understand it up to this point, and then we'll get started on part C, which is the last part of example 6, where we're supposed to calculate f of x plus h. So I'm actually going to give myself some more room. I have to kind of write big on the screen. But this is 6c. Okay, and just so I don't have to flip back, I'm going to write the original function. So the original function given to me in the directions was f of x equals negative 2x squared plus 6x minus 3. And in part C, I'm asked to calculate f of x plus h. So again, that means that everywhere I see an x in the original function, I'm going to replace it with x plus h. So negative 2 times x plus h squared plus 6 times x plus h and minus 3. Now I'm going to take this and simplify it in a very similar manner to the way that I simplified this one. Okay, so let's do that now. That gives us negative 2 times x plus h times x plus h, carrying the rest of it down, plus 6 times x plus h minus 3. Again, I am going to FOIL that part. So negative 2 times front, outer, inner, last. X times x is x squared. X times h is hx. Always put your variables in alphabetical order. It's just a little trick of the trade to make sure you can see like terms. Okay, so x times h is hx. H times x is also hx. H times h is h squared. Okay, carrying the rest of it down, plus 6 times x plus h minus 3. So again, just like we did in part B, we will now distribute the -2 to its set of parentheses and the 6 to its set of parentheses. So -2 times all of those things and 6 times these two things. Okay, so -2 times x squared is -2x squared. -2 times hx is -2hx. -2 times hx is -2hx. -2 times h squared is -2h squared. 6 times x is 6x. 6 times h is 6h. And I carry down the -3. So as a final step, I will just combine any like terms that I have, which quite frankly, I think that these two right here are my only like terms. So looks like we get -2x squared minus 4hx minus 2h squared plus 6x plus 6h minus 3. And there you have it. As always, rewind the video if you need to hear the explanation again. But for now, let's go on to example 7, which is very similar. Okay, example 7 says evaluate the function h of x equals square root of x plus 3 for the given value of x. Okay, so for A, we are asked to calculate h of 22. So we'll plug in at 22. Square root of 22 plus 3. 22 plus 3 is 25. Square root of 25. And that simplifies to 5. So our answer is 5. Easy peasy. Okay, let's take a look at this one. This one's going to seem complicated, but it's actually pretty easy. We are now calculating h of a minus 4. Okay, so everywhere I see an x in the original function, I'm going to replace it with a minus 4. So this is actually the square root of a minus 4 plus 3. Because again, all I'm doing is replacing this x right here with whatever's in the parentheses. And in this case, it's a minus 4. So now to finish, I'll just combine like terms. So -4 plus 3 is -1. So this is square root of a minus 1. And that is as simple as it gets. So that's your answer. All right, and last but not least, we have h of x plus h. So h of x plus h. Now, this is actually the easiest one, but it looks the most complicated because of that double h there. But it's super simple because we're just replacing the x in the original function with x plus h. So instead of square root of x plus 3, we simply have square root of x plus h plus 3. And that cannot be simplified anymore. So that is our answer. And that's enough of plugging stuff into functions. Let's go ahead and move on to our next set of critical terms. So it says, given a function defined by y equals f of x, the following are true. The x-intercepts, that's your first blank, the x-intercepts are the real solutions to the equation f of x equals 0. The y-intercept is given by f of 0. Let me give you a shorthand way to say that. If you are asked to find the x-intercept, you're going to let y equal 0 and solve. That's what the first bullet point means. If you are asked to find the x-intercept, you're going to plug in 0 for y and solve. Conversely, if you are asked to find the y-intercept, you're going to plug in 0 for x. So for the x-intercept, you let y be 0. For the y-intercept, you let x be 0. And solve. Okay, so keep that in mind as we go into example 8. All right, it says determine the x and y intercepts for the given function. Write your answer as an ordered pair. If there is more than one answer, separate your answer with commas. Okay, so they give us p of x equals negative x squared plus 18. So let's find the x-intercept first, where we're going to let y equals 0. So remember, in a function, the f of x or p of x or h of x, whatever this part is over here, that's your y. Okay, so another way to write that function would be y equals negative x squared plus 18. So when we say we're finding the x-intercept, we're letting y be 0. What we actually want to write is 0 equals negative x squared plus 18, which is the same thing as negative x squared plus 18 equals 0. And now we're going to solve it out. Subtract 18 from both sides to get negative x squared equals negative 18. Divide both sides by negative 1. X squared equals 18. And then we're going to square root both sides. But we know that when we square root both sides of an equation, we have to put a plus or minus in front of the numerical side. So that means we get x equals plus or minus the square root of 18. Now that can be simplified because 18 has a perfect square that goes into it. Another way to say that is that 18 can be written as 9 times 2, and we know the square root of 9. So if 18 can be written as 9 times 2, then the square root of 18 can be written as the square root of 9 times the square root of 2. And we know the square root of 9. The square root of 9 is 3. So that means what we have in simplified form is x equals plus or minus 3 square root of 2. Okay, so since we have two x values, that means we have two x-intercepts. The first x-intercept is 3 root 2 comma 0. And the second x-intercept is negative 3 root 2 comma 0. And every year I teach this lesson, I always get this question, where do we get the 0 from? Well, remember, an ordered pair is an x value and a y value. The x value is what's down here. The y value, remember, y was 0. So 3 root 2 comma 0, negative 3 root 2, oops, didn't mean to move that, comma 0. Okay, so we still need to find the y-intercept. So let's do that now. We'll do it in blue. So the y-intercept is what we get when we set x equal to 0 and solve. So we're still wanting to use this equation up here because that's the one that was given to us. Y equals negative x squared plus 18, but we'll put 0 in for x this time. Y equals negative 0 squared plus 18. Well, 0 squared is 0, and 0 is not positive or negative, so that's just y equals 0 plus 18, or y equals 18. And again, we want to do x value, comma, y value when we write our point. So this time, the x value is 0, the y value is 18. So the point is 0, 18. Now, I'm pretty sure in ALEKS, when you go to do this homework, the way that they want this answer written is they want all of these points, like both the x-intercepts and the y-intercept, just written as a list with commas. So, for example, you could write it like this for your final answer. 3 root 2 comma 0, comma, -3, root 2, comma, 0, comma, 0, 18. All of those x and y intercepts just listed together and separated by commas. Okay, let's do another one just to make sure that we have the concept of the x and y intercepts. Okay, so let's take a look at example 9. Now, this would be a great place for you to pause the video, try example 9, and then once you have your answer, you can play it and listen to my explanation to see if you got it right. So let's see. Determine the x and y intercepts for the given function. Write your answer as an ordered pair. If there is more than one answer, separate your answers with commas. So again, same directions, just a new function. S of x equals the square root of x minus 2. So remember, this is the same thing as y equals square root of x minus 2. So now we're going to find the x-intercept, which is where we let y equal 0. Okay, so that would be 0 equals the square root of x minus 2. That's the same thing as the square root of x minus 2 equals 0. Adding 2 to both sides, I get square root of x equals 2. And then to get rid of a square root, I would have to square both sides. Okay, so that gives me x equals 4. So I only have one x-intercept because I only got one x value. So remember, the point is x comma y. So the point would be 4 comma 0. All right, and now let's try the y-intercept, which we get when we set x equal to 0 and solve. So y equals the square root of 0 minus 2. Well, the square root of 0 is 0. So y equals 0 minus 2, or y equals -2. So 0, -2. Okay, so it looks like for this one, I got one x-intercept and one y-intercept, which is fine. Alex is just going to want you to put those two intercepts separated by a comma. So 4, 0, comma, 0, -2. Okay, and that's it. All right, so let's do a little practice with domain and range. Example 10 says, determine the domain and range of each function. Give your answers in interval notation. So we've already discussed that the domain is the set of all x's, which the x-axis runs from left to right. So if I'm looking at a graph and I'm asked for the set of all x's, I'm looking from left to right. Range is the set of all y's. Well, the y-axis is vertical. So I'm not looking left to right when I'm looking for range, I'm looking up and down. So you can think of the domain as lowest x value to highest x value, and then you have to consider if there are any breaks or anything in between. And then you can think of range as lowest y value to highest y value, again, just taking into consideration if there are any breaks or anything in between. Okay, so let's take a look at this. Let's look at part A. So the domain. Well, if I look all the way to the left, the lowest x value I see is this one right here, which is -3. And I notice that there's an open circle on -3, so that means it's going to get a parenthesis. Remember, open circles get parentheses, closed circles get brackets. And if there's a line through it and there's no distinct open circle, you can just assume that it's closed. Okay, so the lowest x value I see is -3. But then there's not a highest x value, because it points forever to the right. If your arrow points forever to the right, that means your domain goes to infinity. And guess what? positive and negative infinity also always get parentheses. So it looks like our domain is from -3 to infinity, meaning that it begins at -3 on the left in reference to the x-axis, and then it goes to infinity or continues to go right forever and ever. Let's look at the range. Okay, so similarly, looks like this is the lowest y value that ever exists, and that's -2. Again, that's an open circle, so it'll get a parenthesis. But then this arrow right here, not only does it go forever right, it also goes forever up. So the fact that that arrow goes forever right tells me that the domain goes to positive infinity. The fact that that arrow goes forever up tells me that the range goes to positive infinity. So for 10A, the domain is -3 to infinity, that's left to right. The range is -2 to infinity, that's low to high or down to up. Okay, let's take a look at this one. This arrow points forever to the left and it points forever up. Keep that in mind. Then we have a filled in circle stopping here. So let's talk about our domain first. Okay, well, it goes forever to the left. Forever to the left means that my domain begins with negative infinity. The fact that I have an arrow pointing to the left tells me that my domain begins with negative infinity. And then I can trace the function. There are no breaks or anything in it. But the highest x value that I ever get to is 4. That's this one right here. So I know it's going to go to 4, but that particular point has a filled in circle, so I'm going to put a bracket. So my domain is from negative infinity to 4 with a bracket. Now let's talk about my range. The lowest y value that I ever hit seems to be right here at -4. So my range is going to begin with -4. Now I'm going to erase the dot that I just put there. But do you see how there may not be a clear closed circle, but it's not an open circle? The fact that it's not open tells me that it's closed. If it were open, it would be very clearly and distinctly open, like this one. The fact that there's not an open circle here makes me assume that it's closed. So I'm going to go ahead and give that 4 a bracket. And then the fact that that arrow goes forever up again tells me that my range goes to positive infinity. So for 10B, my domain is negative infinity to 4, where 4 has a bracket, and my range is -4 to infinity, where -4 has a bracket. All right, let's take a look at C, last domain and range example. And we're almost finished. I promise we're getting to the finish line, but the nice part is this is a video, so if you need a break, just pause it and come back. Okay, so let's talk about that domain. Well, let's look at these arrows first. This one is pointing to the left and down, right? Whereas this one over here is pointing to the right and down. Now, the words right and left tell me something about my domain because that's the way the x-axis runs, is right to left. The words down and conversely up tell me something about the range. So let's talk about the domain first. This domain is actually pretty easy. You could trace that function. There's no breaks or gaps or holes in it. So the fact that I have no breaks or gaps or holes and I have an arrow going forever left and an arrow going forever right tells me that my domain is negative infinity to infinity. Okay, the range. Now, the fact that both of my arrows are going down tells me that my range starts with negative infinity. However, it goes all the way up to here, and that right there is the highest y value I'll ever get to, and it's a 4. So my range is negative infinity to 4, and I'm going to close that off with a bracket since it's a closed point. So for 10C, my domain is negative infinity to infinity, and my range is negative infinity to 4. So there in example 10, you have 3 examples of how to determine domain and range given a graph. But you won't always be given a graph. Sometimes you'll be given a function, like in examples 11 and 12. So let's talk about the guidelines to find the domain of a function. At this point in college algebra, there are only 2 guidelines you must consider to determine the domain of a function. Okay, first guideline is your first bullet point. Exclude values of x that make the denominator of a fraction 0. Okay? Exclude values of x that make the radicand negative within an even indexed root. Okay, that's a lot to talk about, so I think it would be easier if I showed you this within an example. Okay, so let me give you the short version of this. At this point in college algebra, you're only looking for 2 things. Here's the first one. If you have an x in the denominator, you're going to have a restriction on your domain. That's what the first thing you're looking for is x's in the denominator. 2, if you have an even indexed radical, so that's like a square root, 4th root, 6th root, 8th root, stuff like that. Okay, so let's take a look at example 11 because some of this is going to be easier to understand within examples. So just pay really close attention. It says, write the domain of each function in interval notation. Okay, so let's look at 11a. R of x equals x squared minus 3x minus 28. There are no x's in a denominator position, so I don't need to worry about number 1. And there are no square root symbols. So that's just a quadratic, which we'll study later. But my point is, I don't have any x's in the denominator, so rule 1 doesn't apply. And I don't have any square roots or 4th roots or 6th roots, so rule 2 doesn't apply. So I can automatically assume that the domain of A is negative infinity to infinity. But now let's look at 11b because it's going to show us what we need to do when we do have an x in the denominator position. How do we figure out the domain when there are x's or a single x in the denominator position? So g of x says x plus 2 over x squared minus 3x minus 28. Well, when it comes to the domain, I don't care about the numerator. I care about the denominator because we've learned since we were really little that we can't divide by 0. So I know that the denominator can't be 0. So let's write that out. X squared minus 3x minus 28 cannot equal 0. So we're going to have to factor that to figure out what values would make the denominator 0. So I asked myself, what 2 values multiply to give me negative 28 and add to give me negative 3? And the answer is negative 7 and 4. Negative 7 plus 4 is negative 3. And negative 7 times 4 is negative 28. So x squared minus 3x minus 28 factors into x minus 7 times x plus 4. So I factored that, and I now have x minus 7 times x plus 4 cannot equal 0. So that means x minus 7 cannot equal 0, and also x plus 4 cannot equal 0. So if I add 7 to both sides, I get x cannot equal 7. If I add 4 to both sides, subtract 4 from both sides, I get x cannot equal negative 4. So putting those in order, I get x cannot equal -4 or 7. But here's the thing. Those are just the two values that x can't equal. It can equal anything else. So if I think about a number line, okay, I can have anything on my number line all the way from -infinity to infinity. But I'm not allowed to have -4, and I'm not allowed to have 7. That means I can have anything here, or anything here. So taking out -4 and 7 took my number line and it broke it into 3 sections. Well, those 3 sections are the 3 intervals of my domain. So we can say our domain this way. Okay, our domain, and of course this is for part B. I'll write part C in just a minute. Okay, but our domain is the first section, -infinity to -4, in union with, that's how we join the sections, the second section, -4 to 7, in union with the third section, which is 7 to infinity. Okay, so let me get my highlighter out. But this is your domain for part A, and this is your domain for part B. Let's take a look at part C together. Okay, so this is, I'm going to rewrite it. You probably have room, but I have to write really big. You may not though, so use the back of the page if you need to. But this is 11C. We are almost finished. We have t of x is equal to x squared minus 3x minus 28 over x plus 2. So if you look carefully, 11b and 11c are the same function switched, like we switched the numerator and the denominator. But that was to make a point that when considering the domain, we are only worried about the denominator. It's only the denominator, which in this case is x plus 2, that cannot equal 0. So let's write that. X plus 2 cannot equal 0. Subtracting 2 from both sides, we get x cannot equal -2. So that means that x can be anything on the entire number line except for -2. So to find our interval notation, let's put that restriction on a number line just like we did for 11b. So here's -2. This is the -infinity side and the positive infinity side. So remember, the only thing we're not allowed here is -2. We can have anything before -2 and anything after -2. So when we put that restriction of -2 on our number line, it broke our number line into 2 sections. And those are the 2 intervals of our domain. So our domain for 11C is -infinity to -2 in union with -2 to infinity. Okay, so problem 11 in general, A, B, and C, demonstrate the first bullet point. This is how you find the domain if an x shows up in the denominator position. But now let's bounce back to here and figure out how we find the domain with these square roots. This is bullet point number 2. So example 12 says, write the domain of each function in interval notation. So let's look at 12a. We have the square root of 5 minus t. So here's your rule, okay? Let's go up here. Rule 1 was that the denominator could not equal 0. That was rule 1. Rule 2 is that the inside of an even radical has to be greater than or equal to 0. Keep that in mind. the inside of an even radical has to be greater than or equal to 0. So let's look at 12a again. F of t is equal to the square root of 5 minus t. Well, that's an even root, square root. There's an understood 2 right here. So the inside of that has to be greater than or equal to 0. So 5 minus t has to be greater than or equal to 0. So we're going to solve that. If you subtract 5 from both sides, you get negative t is greater than or equal to negative 5. If you divide both sides by negative 1, you get a t and a 5, but when we divide an inequality, the greater than or less than, by a negative, or we multiply it by a negative, you have to flip it. So this is t is less than or equal to 5. And that's the domain. We just have to translate that to interval notation. So picturing a number line again, if this is a 5, we know that our domain has to be less than or equal to 5. So it's anything over here. Now, because it's less than or equal to, we're going to do a bracket. So we would say, remember, this is negative infinity and positive infinity. We would say negative infinity to 5. Okay, so we started to make a little list. I think it was up here. Remember, positive and negative infinity and open circles get parentheses. Also, you can say that greater than and less than get parentheses, but greater than or equal to and less than or equal to get brackets. So 5 got a bracket because it was a less than or equal to symbol, but that would be negative infinity to 5 with a bracket. Okay, now let's look at B, 12b. G of t equals the cubed root of 5 minus t. Now that looks very similar to what we had in part A, but the difference is that's not an even root, that's an odd root. So odd roots don't count. Odd roots have a domain of negative infinity to infinity. So we don't even have to think about this one. It's just negative infinity to infinity since it's an odd root. And now let's look at C. Now C is going to be a little confusing for us because it combines what we did in example 11, rule 1, and in example 12, because we have 6 over the square root of 5 minus t. So we have a square root, which means the inside has to be greater than or equal to 0, but that square root is in the denominator position. So it can't be equal to 0. So since the square root is in the denominator position here, we're going to say that the inside of the square root has to be greater than 0. We're not going to say greater than or equal to. We're going to say greater than 0 because it can't be equal to because the denominator can't be 0. So if the square root is in the denominator position, you're just going to do the inside greater than 0. So 5 minus t is greater than 0. Same process as last time. Subtract 5 from both sides. Negative t is greater than negative 5. Divide both sides by negative 1 and flip your inequality symbol. T is less than 5. Okay, so that's the same thing we had before. So like if we're picturing a number line, it's kind of the same thing, right? So this side of the number line. Only difference is that's a less than symbol, so it's going to get a parenthesis. So we're going to say negative infinity to 5. Okay, so there's a few really good domain examples. Like I keep saying, if you have any questions, go to the math lab or let your professor know. But for now, let's move on to one of the last topics. These will be much shorter questions, but one of the last topics covered in section 1.1, and that's simply about even and odd functions. So here are some formal definitions for you. A function f is even, there's your first blank, even if and only if its graph is symmetric with respect to the y-axis. So that means that you could take the graph and fold it over the y-axis and it would match up on both sides. A function f is odd if and only if its graph is symmetric with respect to the origin. I'll show you what that means when we get to example 14 in a minute. So actually, these two bullet points have to do with example 14. We'll see that in a second. Then we have the last two bullet points that have to do with example 13. And it says if a function f is even, then f of negative x is equal to f of x. And if a function f is odd, then f of negative x is equal to negative f of x. Okay, now let's talk about example 13 first, which is those last two bullet points. They're more formal definitions. I'm going to show you an easier way to figure out whether a given function is even or odd. And we're going to do it by plugging in x equals -1 and x equals 1. Watch this. So example 13 says, determine if each function is even, odd, or neither. Now I have A, B, and C, and I'm going to show you an example of each so you can see what they look like. So A says f of x equals 3x to the 6th plus 2x squared plus the absolute value of x. So first let's plug in f of -1. So that's 3 times -1 to the 6th plus 2 times -1 squared plus the absolute value of -1. Well, -1 to an even power, whether that's 6 or 4 or 2 or whatever, is +1. Okay, so that is 3 times 1 plus 2 times 1, -1 squared is 1, plus, now the absolute value of -1 is +1. Okay, so really that's 3 plus 2 plus 1, which is 6. So when I plugged in -1, I got 6. Now let's plug in +1. That would be 3 times 1 to the 6th plus 2 times 1 squared plus the absolute value of 1. Again, 1 to the 6th is 1, so that's 3 times 1. 1 squared is 1, so that's 2 times 1. And the absolute value of +1 is +1. So we have 3 plus 2 plus 1, which again is 6. Okay, this is what I want you to see, and it's not going to make total sense until you see A, B, and C lined up together, but just follow me for a second. Do you see how when you plugged in -1, you got a +6? And when you plugged in +1, you got a +6. My point is, you got the same answer. If you get the exact same answer both times, then you can say that that function is even. Okay, so if you get the exact same answer with -1 and 1, the function is even. Okay, now let's look at B. K of x equals 13x cubed plus 12x. Let's try it again. F of -1 is 13 times -1 cubed plus 12 times -1. Okay, if you don't believe me, check it in the calculator, but -1 cubed is -1. So 13 times -1 plus 12 times -1. That's -13 plus -12, or you can think about it as -13 minus 12. Either way, you get -25. Okay, now let's do f of 1. Okay, 13 times 1 cubed plus 12 times 1. 1 cubed is 1, so that's 13 times 1 plus 12 times 1. So that's 13 plus 12, and we get 25. So let's examine these answers again. Let's highlight them. This time, our answers are very close to one another. We have negative 25 and positive 25, but they're not exactly the same. They're the same answer with opposite signs. One is negative, one is positive. That makes this odd. Okay, so let's recap so far. If you plug in -1 and +1 and you get the exact same answer, that's even. If you plug in -1 and +1 and you get the same answer with different signs, that's odd. So now we're going to see part C, but the third rule is if you plug in -1 and +1 and you just get completely different answers, that's neither. So you have even, odd, and neither. So let's try it here. Okay, so we have G of -1 is -1 squared over 3 times -1 minus 4 squared. So -1 squared is +1 over 3 times -5 squared, which is 1 over 3 times 25, which is 1 over 75. Okay, so it looks like when I plugged in -1, I got 1 over 75. Let's try +1. Okay, so 1 squared over 3 times 1 minus 4 squared. So 1 over 3 times -3 squared, which is 1 over 3 times 9, or 1 over 27. Those two answers are completely opposite. I got 1 over 75 and 1 over 27. So since those two answers have nothing to do with each other, I would say that this one is a neither. Okay, so that's how you do even, odd, and neither if you are given a function. But now let's talk about even, odd, and neither if you're given a graph. This is much simpler. You're really just looking at it. Okay, so it says determine if each graphed function is even, odd, or neither. So this is pretty simple. If you can fold it over the y-axis and it matches up on both sides, that's even, because even functions have y-axis symmetry. So we can see that in part A. If you folded this right over this line here, it would match up on both sides. So that means that this one is even. Okay, so even functions have symmetry to the y-axis. Odd functions are a little harder to see, but you'll recognize them eventually. Odd functions have symmetry to the origin. That means that if you take the bottom portion and rotate it 180 degrees, you get the top portion, or vice versa. So think about this curve right here, this one that I'm rolling over with my cursor. If I rotated it 180 degrees, I'd get the bottom piece. Similarly, if I took this piece and I rotated it 180 degrees, I'd get this piece. So part B has what we call symmetry with respect to the origin. That means that it's an odd function. Now part C, it doesn't have symmetry with respect to the y-axis, meaning couldn't fold it over the y-axis, nor does it have symmetry with respect to the origin, so we would just call that one neither. Okay, so again, you have one example of each. All right, and here is our very last concept for section 1.1, increasing, decreasing, and constant. And it is pretty simple. Here's our definitions. It says, these are the formal definitions, but they're not too bad the way that they're written in here. A function f is increasing on an open interval I if the graph is moving in an upward direction from left to right on that interval. A function f is decreasing on an open interval I if the graph is moving in a downward direction from left to right on that interval. And then a function f is constant on an open interval I if the graph is moving in a horizontal direction from left to right on the interval. So let's see what that looks like. Okay, example 15, they're going to give you a graph and they're going to say use interval notation to write the intervals over which f is increasing, decreasing, and constant. So I'm going to go ahead and write those words here: increasing, decreasing, and constant. So when we read a graph, we read the graph from left to right, just like we would read a book. And when you're talking about increasing, decreasing, and constant, you're talking about tracing the graph from left to right. So here's where the graph starts at -5. And when I begin to trace it, my pencil is moving up to here. So I would say that that interval is increasing because when I traced it from left to right, it was moving up. Now, when we list increasing, decreasing, and constant intervals, we always list them by their x values. So I would say this is increasing from x value -5 to x value -3. -5 to -3. And you might say, wait a minute, that was a closed circle. Why didn't we put brackets? Well, we always use parentheses for increasing, decreasing, and constant. And the reason actually goes back to the definition. Do you see how it says an open interval, an open interval, an open interval? The word open tells us to use parentheses. So we're always going to use parentheses on those no matter what. So this first piece was increasing. Then it changes and it begins to just move horizontally to here. So that piece is constant. So I would say that the graph is constant from -3 to -1. Then the graph starts to increase again. And it increases all the way to here, which is at x value 2. So I would say that there's another increasing interval from x value -1 to x value 2. And then after that, it begins to move down and it goes in the positive infinity direction and continues to move down forever and ever. So I would say that it's decreasing from 2 to infinity. Okay, so that's increasing, decreasing, and constant. And last but not least, we have relative maxima and minima, which sort of has to do with things increasing and decreasing. But simply put, you can think of the local maximum and the local minimum as the high points and the low points in a certain area of the graph. You can think of the absolute maximum as the highest point that exists on the graph, and the absolute minimum as the lowest point that exists on the graph. So this says, determine the location and value of any relative maxima or minima of the function. So by the way, local maxima and minima is the same thing as relative maxima and minima. It just means that if you're looking at a particular section of the graph, it's the local high points and low points on that graph. So I would say that this graph, or this section of the graph, has 2 local low points. Okay, this is a low, and this is a low, and 1 local high point. So it has 2 relative minima and 1 relative maxima, or maximum, excuse me. So let's go ahead and write that in sentence form, and then we'll be done. So we're going to say the function has 1 relative maximum. Remember, that's a relative high point at, and then we're going to put the actual coordinate point of this high point, which is 2, 1. So we can say the function has one relative maximum at 2, 1. And then we're going to say the function has 2 relative minima at, and we're going to list those 2 low points. So it looks like the first one right here is at -1, -5. So -1, -5. And the second one right here is at 4, -2. Okay, so those are our answers. The function has one relative maximum at 2, 1, and the function has 2 relative minima at -1, -5, and 4, -2. So that is it for section 1.1. Again, if you have any questions, head to the Math Lab or email your professor, but I hope you got a lot out of it.